In this video, we are going to talk about Unit 5, Topic 4, Analysis of Variance. So in Topic 3 of this unit, we looked at the goodness of fit test, which was determining if more than two proportions are equal. So a similar extension to this from the Unit 4 tests is to determine if more than two population means are equal. And this is actually a really popular test in statistics. So to test this claim, we're going to be performing what's called an analysis of variance test, which is abbreviated as an ANOVA. There are two different major questions that arise when an ANOVA is introduced. So the first one is that if we're trying to see if more than two populations means are equal, how come we don't just run two population mean tests for each group? So how come we don't just run multiple two population mean tests? Well, let's say we have three groups, we'll call them A, B, and C, and we wanted to determine if the means were equal or if some of them were different or they were all different. If we were using two population mean tests, we would need to run three tests. Now, at first, running three tests doesn't seem like very much fun. So that's, kind of one of the things is that the more calculations and stuff we make, the more mistakes that we can possibly make. But that isn't a reason to, not run a test a certain way. But the reality is that the error of our test also compounds, just like the error that we can make if we're running multiple tests with human error taken into account also compounds. So specifically, if we have a significance level of 0.05, then we would have 95% confidence for the overall tests, and our confidence level for all three of these combined is going to be 0.95 to the third power. So that number ends up being 0.857, which is 85.7%. So when we're doing multiple tests, we end up kind of going downhill fast. So this is just 0.95 to the third power. So our overall confidence level would be 85.7%. So not only is it time consuming, but we also end up having a higher chance of making incorrect decisions with the hypothesis test. So this doesn't say this in the notes, but the way that the ANOVA works is that what it does is it sets alpha so that after you've ran the three tests, you end up with an overall confidence level of 95%. So depending on how many groups you have and how many tests you need to run within that to see if the means are equal or not, the alpha level is kind of modified so that there is an overall alpha level of 0.05. So another question that could come up is that if we're testing a claim about means, how come the test is called the analysis of variance? So generally, we kind of associate variation and variance with the standard deviation, but variance is specifically the standard deviation squared. Well, one way, and this kind of gets us back into some Unit 1 thinking, one way that the standard deviation can be thought of is how good of a job the mean does at summarizing the data set. So the standard deviation could be thought of at how good of a job the mean does at summarizing the data. If the standard deviation is large, especially compared to how big the mean is, so for example, if you have a mean of 100 and a standard deviation of 80, then that means that the data is pretty far spread out, and the mean doesn't do that good of a job at describing the data set, because in general, the data is pretty widely spread out around 100. However, if the standard deviation is really small, the mean is going to do a better job at summarizing the data with that single number. So when the standard deviation of a data set is small, we sort of have more confidence at the mean at summarizing the data set. So if the means are close but the standard deviations are all over the place, that's a consideration that needs to be made in the overall picture. So remember, sample size also comes into play, and that has to do with how confident we feel when we're running a hypothesis test. So what's new with this test? Well, the truth is that Stata has a bunch new going on, but the reality is that the assumptions with this test are just an extension of the two population mean test. So the first thing that we're going to check for when we actually have to run something is to see if the normality of the populations passes. So that means that if we have, a big data set and there's three groups within that, we need to check normality for A, check normality for B, and check normality for C. So all of those in a perfect world should pass. And so next we also have an equality of variance assumption, which we did check when we did the two population mean test. And that's to see if the standard deviations from each group are statistically the same or if at least one standard deviation is different. So similar assumptions to the two population mean test, but it does kind of make the test a little bit more stable than running more than one two population mean test. However, the truth is that an analysis of variance isn't sensitive to either of these assumptions. So what this means is that if these assumptions fail, the results of the test aren't affected too much. But passing those assumptions does make the test stronger. So ideally, we want to pass those assumptions, but if they fail, you can still argue the use of that test. There's other tests that don't rely on the normality assumption, but unless this assumption fails in a really bad way, the results for those two tests should be the same. And so then lastly, to visualize an ANOVA data set, we're going to make a box plot for each group on the same axis. So there is a lot going on in STATA as far as an ANOVA is concerned, but the actual hypothesis test itself isn't too wildly new or different. So let's look at our reference tables for Unit 5. So first, testing a claim about more than two means. The null hypothesis is that the mean from each group is the same. So this is pretty similar to that more than two population proportion test. And then our alternative hypothesis is that at least one mean is different. So the assumptions, we get a nice little extra parenthesis in its own assumption here. The samples should be random, although a lot of times this will not pass. The samples should be independent. So again, the passage of this assumption is ideal, but there's a lot of cases where you can argue that the test will still be valid if independence fails. So it's more of just like if the assumptions pass, some of them are deal breakers, but a lot of them it's still okay to proceed with the test as long as you kind of have a disclaimer that your certain assumption didn't pass. So this next assumption, normally distributed residuals, this is the formal assumption for an analysis of variance. We're going to be checking this in a slightly sidestep kind of way by using the Shapiro-Wilk test for each group. So we're going to approximately check this using the Shapiro-Wilk test for each group. And then lastly is the EOV test. This is called the Bartlett's test. And so that's going to be an output of the ANOVA in STATA. So there is a document that has a description of all of these, so we're not going to worry about this here. Your goal for the problems should be just to follow along and then try to recreate them on your own in your without looking at the video and the solutions. So the first problem is how productive are U.S. workers? And this is data from Forbes' top companies. So one way to answer this question is to study annual profits per employee. A random sample of companies in computer field, aerospace field, heavy equipment, and broadcasting gave the following data regarding annual profits per employee in thousands of dollars. Determine if the profits is the same for each field. So our post-hoc test, step 7, is going to be very, very similar to the same tests that we did, except for there's going to be a lot more confidence intervals. We don't need to do more than one test, but it is a little bit more of a space user. So I usually like to just kind of eyeball this first. So looking through, these numbers don't seem to vary too widely. We do have in C some of the higher profits, but we also have some of the lower profits as well. So even though we do have a higher profit here, our mean should be pretty similar to the rest of the groups because the data is pretty far spread out, and so those lows and highs should kind of even each other out. So the first thing is entering your data into STATA is very specific for an ANOVA. And the way that you want to do this, I'm going to take a screenshot because this might look pretty small on your screen, is you want to have two variables. You want to have one for your response variable, which is what you're looking to record, in this case profit. And then you want to have a second variable that has the grouping variable for your data. So the grouping variable is going to need to be a number every time. So for an ANOVA, it actually doesn't have to be, but for our post hoc tests in step 7, it needs to be a number or it's going to have a problem recognizing that. So every time I'm going to put my groups as 1 through however many groups there are. So comparing this data set to the data that was given, I have 5 numbers for A, and those are the first 5 numbers that are recorded here. I have 6 numbers for B, and those are the next 6 numbers that I recorded. 5 numbers for C, and those are the next 5 numbers, and then 5 numbers for D, and those are the next 6 numbers that are recorded. So this data set is in the file for this topic, but I definitely recommend putting in one data set, and the next one is a little bit longer, so if you're going to enter in one by hand, it should be this one. So the next step is to visualize the data. And so this, again, you should be visualizing a lot of things, even if the hypothesis test doesn't demand it. But the hypothesis test is based off from the middle and the spread of the data. So I usually like to try to get a picture on this one since I can't easily visualize 4 different groups. So you're going to go to graphics and then box plot. And for your variables, you're going to put your response, which in my case is profit. We don't want that twice. And then you're going to put in a by variable. And you're going to check this box up on top. And then under the variables, under the by tab, you're going to put your grouping variable. So whenever you have different groups, if the data is in one column, you're going to need to use a by variable. So when you hit OK, you're going to get a bunch of squares. So remember this line here on a box plot is the median. It's not the mean per se, but this is going to, give us a way to eyeball how spread out the data is. So there's also not a very large sample size. So this is literally the lowest number, the next lowest, middle, next highest, and the highest number of the data set. But when comparing these in general, since this axis is the same, I don't really think that we're going to find the data has a different mean, even though this data set is a little bit skewed upwards. So group 1, which is the computer group, they're a little bit skewed upwards. So another way that you can look at this is just getting the descriptive statistics for each group. So that's going to be done a very similar way. You're going to put in a by variable. And so this gives us out a table. And so looking through here, the means, they do vary. 17.28 is the highest mean. 11.57 is the lowest mean. But also these standard deviations, so this is the highest, but it also has the highest standard deviation. So this is the lowest mean, and it has a smaller standard deviation. So, I mean, I don't think, especially because of the sample size, I think it's going to be pretty hard to determine that these are different because they're all pretty much in the same ballpark. So the first thing that we want to do is set up our test. So our HO and our H1 are going to be that the means are all different, or I'm sorry, that the means are all the same. So 1, 2, 3, 4. And I have my 1, 2, 3, 4 out here. So since these are labeled up in the problem, you don't need to label them specifically. But with the next problem, there's not going to be numeric labels, so you should make sure that you are as clear as possible with that. Our H1 is that at least one mean is different. So now for our assumptions, we've got a little bit more going on. And again, as what usually happens is we really can't check this assumption until we've run the hypothesis test. So random, they don't specify that. Independent, I don't necessarily know if I would pass this. If some of them were part of the same year and other ones weren't, you would worry that there'd be kind of similarities with economies for those two different groups. But again, if it's pretty vague, a squiggle is okay for this assumption. So each group needs to be normally distributed, and then the standard deviation for each group should be equal. So I've passed these already because, I've already ran these. But we're going to check the first of the bottom two here to see if we pass normally distributed data. And then we won't get this next one out until we actually run the ANOVA. So we're going to run the normality test the same way that we've done before. So you're going to select the Shapiro-Wilk normality tests under the distributional plots and tests. And then you're going to again put in your response variable and then put in the by variable. So we get a pretty similar looking output, except for this is the Shapiro-Wilk test for each of these groups. So here is group 1, here is group 2, group 3, and group 4. So since all of these are higher than our typical threshold of 0.05, then we have no evidence to fail normality, so we're going to pass that assumption, which is what has happened here. And so then now we're going to run the ANOVA test. Our step 7 is actually another test after that. Running the ANOVA is going to be under the statistics menu, and it's the same option as regression for this next menu, except for when we get down here, we're going to select ANOVA / MANOVA. It's multiple trials for each group is a MANOVA, and then we're going to select a one-way ANOVA. Just as we did before, we're going to select the response variable, except for now the factor variable is actually going to be where we're going to put our grouping variable, not in this by. So this is if we actually have two separate grouping variables. So we don't need to click anything else. You just have to put your response here, your grouping variable here, and then hit the OK button. So the output for the ANOVA test has a bunch of stuff going on, but what we only need here is this test statistic. It's an F score, so we've seen the F distribution before. This is our p-value, and then we also need this p-value down here, which is for the EOV test. So these three components are going to go into our assumption and our hypothesis test. So this first, the p-value is 0.28, higher than 0.05, so that passes that we have equal standard deviations. Our F-score was 0.85. The p-value was 0.4867, and this p-value is higher than anything that alpha is, so we failed to reject HO. And then we conclude that all of the means are statistically equal. So what we expect to see is if we didn't reject HO, our emphasis would be 0 in a two-population test. And we're going to find that that same thing is true in the ANOVA test. So in our data, we're going to go to summaries, tables, and tests, summaries and descriptive statistics, and then we're going to select pairwise comparisons of means. So in this menu here, we need to select our variables, and then we also need to select Tukey's method from this multiple comparisons adjustment. And as mentioned before, this is when the test ends up affixing or changing that alpha value so that after all of the tests are done, it ends up having a significance level of 0.05 and a confidence level of 95. So response, grouping variable, and then Tukey's method. So when you hit OK, you're going to get a confidence interval for every pair. So it has 2 and 1, but it does not have 1 and 2 because those are going to be, the same thing but flipped. So the way that I write my step 7 here is I write what each of the pairs are with each of their confidence intervals. So the output for 2 versus 1 has a confidence interval that goes from negative 15.9 to a positive 4.5. So that's where I end up with negative 15.9 to a positive 4.5. And I repeat this for each of my groups. And so what this is going to do is it's going to show whether or not we support our conclusion. And so since 0 is inside all of these here, we have a sign change for each one. Since 0 is in all of them, then that means we're going to determine that all of the means are statistically equal. So that goes to say that if we don't have 0 inside, then we would conclude that the pair that we have was statistically different. So I'm going to leave the next problem up to you. There's also going to be a Unit 5 practice that will have one problem from each. So please make sure you work through these problems. You'll see when the final exam information is posted that you will not be using Stata on your final exam. So you will be responsible for seeing an output exactly how it was given to you on the sheet. So you can be responsible for seeing the output for these tests and being able to interpret them, but you won't have to do an ANOVA from complete scratch. But I would still make sure that you know how to, do the motions, because the more familiar you are with Stata, the more easily you'll be able to interpret the output.